So in Lecture 7, we're going to jump right into covering some more of dipole moments, right? And so this builds on some of the earlier stuff that we discussed of what dipoles are attributed to, right? And so what we said originally in the early days, that dipole was explicable by electronegativity. So if we have something like ethane, okay, and we contrast that to something like methylamine, and we contrast that to something like methanol. All right, and we're starting to run out of space here, but I can just scoot this over, and I wonder if I can. Ooh, I can even shrink it. Wow. Methanol, and we can contrast that. Boop. Let's delete that. Contrast that to chloromethane. So, all right, and what you've noticed here is this is a general trend of the electronegativity of the attached atom increasing as you go that way, right? And so this has no dipole. If you can imagine putting a mirror up here in between these two things, you'll know that this is just a reflection of itself, so there can't be a dipole, and that is essentially non-polar. But as you increase the electronegativity, you start producing a stronger polarity in the molecule, right? So chlorine has a very clearly a stronger level of polarity, and these actually can be measured, so you can measure the polarity, and the actual measured units of polarity are the debye. And that's spelled like D-E-B-Y-E-S as there. All right, and the unit is just D, okay? And so the molecular dipole moments of molecules can be essentially relegated to as a scale. I don't know if there's an absolute scale, like it goes up to a certain number, but at the very beginning. So the dipole moment of some common molecules as you start replacing it. So we've said that chloromethane is polar, right? So if we were to draw all this out, where does all that polarity come from? All right, so we've got something here, and this is an H, 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 right? You look at the electronegativities associated with the H's, and you'll notice carbon is modestly maybe more electronegative than hydrogen. They're very close though. And carbon chloride has a very large difference in polarity. That difference is actually this molecule has a dipole moment of 1.9 debye. Okay, and that can of course increase a lot if you start replacing the hydrogens with chloride. You can then start putting a bunch of Cls on here, right? And that molecule is actually called chloroform, and you've got a lot of polarization here directing you with an overall vector to the right side of this screen, and it has a polarity of 1.0. Now, why? Right? Why did it go down? Well, you gotta keep in mind these molecules have geometry. They have shape. This is a tetrahedral molecule, okay? So if I were to draw it more shape conscious, put a chloride here and then put my H here and then an H down there and then an H coming out towards you. And then let's look at what it looks like with chloroform. And you end up with an H here, okay? So you have essentially a huge dipole associated with it going in this one direction. All of the electron flow is in this direction, whereas you have it tugging upward. You have it tugging a little bit to this side, and you have it tugging like a little bit towards the back. So your net dipole in chloroform is actually now scattered in several different directions, really, right? And so, whereas in this one you have all that one's going back into the plane, that one's coming towards you, actually. And then, so your net dipole is actually higher than this one, okay? And that's a consequence of the three-dimensionality of these molecules. And you can even imagine that in something with a fixed rotational barrier, or a fixed rotation, is going to induce some polarity as well. So let's look at the cis configuration of dibromo ethene. Okay, so what's that? So this obviously has a double bond because I said it was cis, and I said dibromo, so you can assume that there's two bromines, and they're cis to each other. And what you see here is actually a dipole moment that's flushing electrons from here and here, and a dipole moment that's pushing them out quite hardly towards the PR, right? And so that is clearly there's a dipole moment that's going in that direction through the molecule. So this cis configuration has a dipole moment that is equal to 1.9 Dibromo. And you can be sure that the trans configuration with the bromide here, and of course because it's trans, the bromide on this side must be on the other side of the molecule, right? So these are two different molecules. They don't interconvert, but ultimately you have a dipole moment here, a dipole moment that's big over there, a dipole moment that goes in that way, and then a big dipole moment that splits it that way. If you add all the net vectors up, what do you think the dipole is? All right, you can say it inside your head. Hopefully you come to the same conclusion I do. That if you have all the dipole moments all going in opposite directions, then they're going to add up to 0, right? So these are all fairly straightforward. I mean, you can just start drawing your dipole thingamabobs and your little arrows, right? And so this little hooky arrow right here, this is sort of got a standard nomenclature, right? So that's a positive charge. And then we always point arrows in the direction of the electron flow. And so it goes this way. And I know that's the opposite if you've taken physics, because for some reason physicists like to follow positive charges. But, you know, I guess there can be this big physics fight about how you follow charges. But it makes more sense because the electrons are the things that are moving around, not the holes. That doesn't make sense at all. Now, we really looked at actual physical locations of actual atoms, but we gotta remember that lone pairs on these atoms actually they exist, and they exist in specific geometries, right? So if I were to write this molecule here, right, and it's got a lone pair, and we can even draw geometry here where we've got a hydrogen in the back and then a hydrogen coming out towards you. Okay, so this is as polarity, right? It's not a big deal. I can draw the lone pair as sort of its lone little orbital, little lobe up there. That's an sp3 lobe, of course, because this is an sp3 hybridized molecule. There are no pi bonds here. But the lone pair, right, that's just electrons, just like naked electrons. And so there's a dipole in ammonia that is going to push, and of course the nitrogen is now a bit more electronegative than the hydrogen at this point. So you end up with a very clear dipole, right? And so in this particular case, the dipole is 1.5 Dibromo, and it gets stronger as the atoms get more electronegative, and the atoms actually start developing more lone pairs, right? So we all know water is quite polar. It's sort of the prototypical polarity, prototypical polar solvent, if you will. And of course, believe it or not, there are things that are more polar than water. But yeah, see, you got two arrows that point up, and then you've got two lone pairs that point this direction, two lone pairs pointing upward. Of course, this is going to give you a slightly higher polarity than your ammonia, which is now 1.9 Dibromo, right? So this is ammonia, and this is water. All right, and acetone. So let's draw acetone. CH3, acetone has this, what I've been calling a carbonyl in the middle, which is a double bond, carbon double bond oxygen. Oxygen here has now two lone pairs again. All right, and you can really see, so the carbon and carbon and carbon and carbon, you know, not a whole lot of pull between these two same electronegativities, but the carbon-oxygen, there's a big electronegativity difference there. And you also have from this oxygen the directionality of these lone pairs. So there's actually a fairly substantial number of places where you can start drawing a dipole with acetone. And so the dipole of acetone is actually 2.9 Dibromo. All right. And believe it or not, there are molecules that are more acidic than acetone even. All right. Acetonitrile, CH3, CN. All right, and that has a lone pair. Now carbon has, I've drawn two bonds, and I've drawn one bond to nitrogen. So in order to make full octets, acetonitrile has a triple bond to that nitrogen, okay? And now what's interesting is a triple bonded nitrogen is going to have its lone pair pointing directly out. Let me draw that a little cleaner here. It's going to have its lone pair pointing this way. So this is like a totally linear molecule. All right, so this carbon nitrogen got a dipole difference from electronegativity. This nitrogen has a dipole from just having its lone pair pointed out that way. So these two dipoles are completely directional, all facing this exact same direction. You add them all up together, that gives you actually a really strong dipole moment of 3.9 Dibromo. So that's a very polar solvent. And that solvent is acetonitrile. Okay? So lone pairs contribute quite strongly to the interactions between molecules. And you can see once you start building polarity in, right? So how are these things going to start orienting? You just envision them like little magnets. So an acetonitrile molecule is going to want a second one is going to want to point its little electrons directly toward that end, right? It's going to want to be right there. So this sort of starts giving you additional ways of interacting. Because if you imagine these like little magnets, then the little magnets are going to want to align. So we already discussed bonding and the concept of electron sharing as in covalent bonding. But there are other ways of bonding that molecules can sort of exchange or they can interact with each other. There are several what are called intermolecular forces. All right, so intermolecular forces are forces that occur between different molecules. And when you have, depending on the strength of those forces, these can affect the melting point of stuff, right? So if they have really strong intermolecular forces, these things are stuck together super tightly, they're going to want to be a solid. Or if they're a liquid, right, then if they're stuck together really tightly, they're going to affect the boiling point because they don't want to turn into a gas because they like being in a liquid where they can exchange these intermolecular forces. And we already kind of discussed one of them, And we'll do a classification because there are several. All right, and we kind of alluded to the first one, which are dipole interactions, or dipole-dipole forces. Okay, so dipole-dipole forces are what we kind of discussed up above. There's another one called London dispersion forces. Okay, and London dispersion forces are an interesting and important class of forces, right? So you imagine pentane, right? Pentane is 2 carbons, 3, 4, 5, right? And that's CH3, CH3. Remember, there are carbons at the ends and the bends. 1, 2, 3, 4, 5, right? And if you start drawing mirrors around this, you can see like, oh, there's no actual dipole here. That's interesting. So how does a solution of pentane remain a liquid? How do those molecules, how does this pentane and this pentane how do they want to stay in solution together? Because pentane, maybe it's a low boiling liquid. It's a liquid. You can buy tubs of pentane. Sometimes you can buy mixtures of them called petroleum ethers. How do they want to stay in solution? And it comes down to these London dispersion forces. So if you have some molecules and these molecules start getting a little closer together, right? So there's a teeny tiny dipole with a carbon hydrogen and a teeny tiny dipole here. These can start to form sort of transient dipoles between each other. So essentially, while these molecules themselves don't have permanent dipoles, small transient dipoles where the electrons in this carbon will kind of go this way, and the electrons in this bond will go this way. And I know I've drawn them opposing the electronegativities, but the electronegativity difference between carbon and hydrogen truly is not huge. And so because you can sort of induce what we'll call them are induced dipoles, they're induced by being in close proximity. So as you can imagine, they're not strong. But all molecules, unless they have an explicit dipole that repel each other, can induce dipoles where they come together, and really, if you want to think about it, we'll even invoke our friend the nucleus as to exactly what could be happening here. You could have a nucleus here, and you've got the electrons zooming around here, and then there's a nucleus on this carbon over here, right? And then there's the electrons over here. And so normally, like, if they happen to be aligned just like this, and this is your nucleus, and the electrons are sort of mostly on this side of the nucleus at this particular moment, and the electrons on this nucleus are mostly over here on this side of the moment, right? They've actually created a dipole, because then these electrons are like, hey, look, a nucleus. That's cool. And then these electrons over on this side, maybe there's another thing over here. There's a nucleus over here, and there's like an electron cloud, and that electron cloud's sort of like over here, and they can be like, oh wow, look, a nucleus over here. Of course, this electron, you'd be like, whatever, I do what I want. And you can go over here, and then this thing's like, oh god, let's go away. That is, of course, the problem with these London dispersion forces, is they are weak. Right? It's just relying on the fact that a couple of atoms getting together can agree to set aside their electron differences and form a temporary dipole thing that, all one has to do is just send an electron. Of course, I'm obviously giving these things personalities, but it's really, statistically possible for them to be aligned, and also unlikely for it to happen at any great length of time, which means that London dispersion forces and induced dipoles are transient and temporary. So you can imagine them as, things that hold solutions of nonpolar things together. But they are certainly important forces, and they are an important part of what we discuss in this class. Now there's another one, of course, that is a sort of an exchange of atoms, and that is hydrogen bonding. It's not an exchange of atoms, it's sort of a partial exchange of a hydrogen to form a hydrogen bond. So a hydrogen bonding, that obviously requires a hydrogen, and it obviously doesn't occur on a CH bond, because carbon and hydrogen have very similar electronegativities, and carbon is loath to give up that hydrogen. But alcohols, right, and in H groups, right, these have hydrogens, and these have shown some interest in essentially letting them go. So exactly how strong is a hydrogen bond? Well, that's a toughie, isn't it? Right? So, carbon-hydrogen bond. Well, a hydrogen bond, let's just say it can be quite strong. All right. So, what's a hydrogen bond? Very clearly, before we start relegating and defining. So, in order for a hydrogen to start donating to something, there has to be a receptor. Okay. And so, if we draw water, and this is probably something you got from Gen Chem. If we draw water here, you know, there's a lone pair here, and then there's a lone pair here. And if you're a hydrogen and you just like, you know, I love oxygen. I'm polyamorous when it comes to oxygen. I will love on any oxygen. And the thing about oxygen, of course, that it likes are those lone pairs. So this hydrogen right here is like, ooh, a lone pair. And this oxygen doesn't really mind. All right, so this hydrogen can start bonding to this water molecule, and this hydrogen, well, we'll call it covalently stuck to that water molecule. And this interaction right here actually has a fair amount of associated energy. That's why water has a pretty high boiling point for such a small molecule, is because these associations are pretty strong. And more importantly, they can form networks, and they can bounce around. And in a solution of water, obviously, there's going to be a bunch of lone pairs, and so the hydrogens of the water can really start interacting very strongly. Now, the actual strength of a hydrogen bond can be pretty weak, right? So if we consider what a carbon, just as a comparison, if we consider the strength of a carbon-hydrogen bond via its bond dissociation, so the standard enthalpy change when we start breaking things, that's like 410 kilojoules per mole. All right. Hydrogen bonds, you know, they, well, some of them can be pretty weak, like 1 to 2 kilojoules per mole. All right, and so that's like London dispersion forces weakness. That's not very great. They can also be pretty strong. So stuff like they can also be pretty strong, and so you can get upwards of 10 to 100 kilojoules per mole. And of course, 100 kilojoules per mole would be in the very strong, anomalously strong hydrogen bond range, but 10 kilojoules per mole, that's enough to start stabilizing liquids and solutions and actually starting to make a difference, okay, in how things are associated. So let's look at hydrogen bonding in other solvents, or exactly what that happens when you have a good hydrogen bond donor. All right, so we often talk about hydrogen bond donors in the sense that they have to have a hydrogen bond to donate. So ethanol is most people, a lot of people like ethanol. It's a hydrogen bond donor. All right, and it's got a lone pair. And a solution of ethanol actually has a boiling point of 78. Because ethanol not only has that hydrogen there, but it's also got its own set of acceptors, right? So these lone pairs, hydrogen is like I imagine it's just a proton, it's a positive charge, and so it can form like these networks like in water, albeit, water has 2 hydrogens, and so it can do all kinds of shenanigans to make networks of interconnected waters. Ethanol, it's kind of got this big greasy tail, so it's not as well stuck together as water, so it's boiling point 78 degrees as opposed to 100, But contrast it with a molecule that has no hydrogen bond donors. It has hydrogen bond acceptors, which is what I would call these lone pairs. I'd call these the acceptors, and that's what they are called. But if you look at a molecule like diethyl ether, all right, so diethyl ether, which is CH2, and then it's got an oxygen here, but instead of having a hydrogen on the other side, it's just got CH2, CH3, right? So an alcohol has a proton, and an ether doesn't have a proton. This is called an ether, and so it just goes carbon, oxygen, carbon, right? And the boiling point of diethyl ether is 35 degrees Celsius, all right? It's about 34.5, but 35 degrees Celsius. So you can see just how much of a difference that H makes, right? And you can say, oh, well, diethyl ether is a bigger molecule. It also can, you know, it's got like, it's participated. How much of that is due to the fact that, you know, now you've got extra bits of greasy that you've got London dispersion forces, maybe that. So, okay. So if you imagine a molecule of roughly the same size, so this is diethyl ether. All right, sure. What about dimethyl ether? So dimethyl ether is roughly the same size as ethanol. All right, what's the boiling point of that? Of dimethyl ether? Make a guess in your head. Did you guess that? Negative 25 Celsius, right? So having these hydrogen bond donors as a place to sort of share the load, if you will, really helps a lot. Now, hydrogen bond donation ability, having something to do with electronegativity, is, of course, an important aspect, right? So ethanol, right here, that's got a pretty good electron. I mean, that's an electronegative atom right there, oxygen. So oxygen doesn't really mind giving up that hydrogen to start donating. But what happens when you use something that's a little less electronegative, right? So let's say you have ethylamine, CH3CH2 NH2. So this, of course, has two hydrogen bond donors, and it's got a lone pair. Except the big difference here is that the nitrogen is a bit more attached to its hydrogens, so it's not going to want to donate them out so much. So if we compare the boiling point of ethylamine, it's going to be 17 degrees Celsius, okay? So it's quite a bit lower than ethanol's 78 degrees Celsius. And that's really reflective of its poorer hydrogen bond donating ability. All right? And so, what does this all mean? So, in the context of these molecules actually interacting with each other, they induces a higher boiling point. So we've talked a lot about how these interactions promote increasing intermolecular forces where all the atoms are the same, but this polarity does actually change how these molecules can interact with other things, right? So, you know, what are some of the effects of polarity, right? And, well, a big one is, of course, solubility, right? And we got to remember, like dissolves like, all right? Nonpolar things have a hard time dissolving polar things, right? So that's a good way of thinking is polar solutes, all right? So polar solutes dissolve in polar solvents, which is another way of saying if you want to dissolve something if you want to dissolve a molecule, obviously if it's going to dissolve, it's a solid. so the polar solute is going to dissolve, then it needs to go into a polar solvent, right? So if you're going to throw in a polar molecule, something like what's a good polar molecule? You're going to throw in, let's just say this naphthalene compound, OH, right? So that's going to be, you're going to probably want to throw that into a polar solvent. And of course, if you're going to mix two liquids together, then you probably should appreciate that they're going to have to be two polar liquids will mix together and form a dispersion, right? And one polar, one nonpolar, they're going to separate, and they're going to form two phases. Now, how does this? How do once you dissolve something, what does that dissolving look like, right? So if you have, say, acetone. So acetone as a polar molecule, right? But it's got this like apolar bit. But as a polar molecule with a strong dipole moment, it has the ability to dissolve some salts. In fact, it actually can dissolve sodium iodide, right? So sodium iodide. All right, and sodium and iodine are, well, they're not super friends. You know, both sodium and iodide would just love to be separated from each other. Sodium chloride, you know, at least in that particular case, the sodium and the chloride can sort of see eye to eye, but sodium iodide, not so much. It's stable. You can put it on a table and it'll be happy. But what this iodide really just kind of wants to be alone. It wants to go do its own little loner thing. Now, that can be facilitated if you're an acetone molecule by coming in and just taking iodine's place. And how does that look? Is basically you have a sodium and you're going to have an acetone here, right? And it's gonna sort of just start surrounding the sodium with acetones. All right, and it's going to surround them from the face of the oxygen. All right, so sodium iodide is a weak enough bonding interaction for acetone to come in, and then the iodine, of course, it's somewhere, right? You can't have a positive charge without a negative charge. So the iodine is out here, not really caring that it's separated from its sodium. Sodium chloride would be a bit upset because chloride doesn't want to be on the butt end of these stupid acetones. Chloride and sodium chloride is not going to dissolve in acetone. But it all is the exact same principle, right? It's this dipole interacting. Sodium chloride, of course, we all know, dissolves in water. And so you can have sodium chloride, and that's the same sort of principle where you have sodium interacting with the oxygen components of water, and that's stabilizing it. And then the chloride, of course, is out here with the protons, or the hydrogens, right? And so that can donate some electron density out here. That makes sense for sodium chloride, right? That's sort of the difference between these. Iodide, you know, it can really just stabilize with the van der Waals or the London dispersion forces. It's quite happy. Because iodide is this huge, huge atom, and the electrons, because they're so big, and the nucleus is so enormous, they love forming transient dipoles, these iodides. They just love transient dipoles. So they're really great at interacting with the butts of acetone. Chloride is a small atom, doesn't really much care for forming transient dipoles. And we'll get to all this a little bit more. The takeaway here is how they orient in solution, right? So if you're going to learn something from this particular aspect of the lecture, it is that the lone pairs love donating themselves, and they actually form a structure, right? They form a defined structure where the cation, because this is essentially the same thing as just writing the cation, whatever it is, it really just wants to be surrounded by the oxygens or the lone pair containing things, and then they will stick their spinach out this way, whatever that is, if that's the butt of the acetone or if that's the hydrogens of the water, it'll form something like this. And you get these really structured solutes, right? So when you dissolve something into a solution, you start forming really structured solutes. Now, if you're hydrophobic, okay, if you're a nonpolar molecule, right, like, well, pick your favorite nonpolar molecule, right? It can be a pentane, right? The pentane, it lacks polarity, and so it's just going to be like totally interacting with itself because of London dispersion forces. And they're forming little transient dipoles. And you can say, well, sodium chloride, like it. If these are forming dipoles, why can't the little negative bit of the dipole start interacting with the sodium? And the thing is that acetone can break up sodium iodide, but the greasy bits of the acetone can't even break up sodium chloride. So sodium chloride is held together super well, which means that the interactions between the sodium and the chloride are just too strong for the pentane to interact with. They cannot break them up. And that really is the foundation of solubility, right? How good is your solution at busting up the bonds that you're trying to dissolve? And sodium chloride, right? That's sodium and chloride. It's an ionic bond, but it's a strong ionic bond, which means you need to have not only a strong dipole, but you also need to have some little part of it that can entertain both the sodium really well and the chloride really well. And so water, those hydrogens can really entertain the chloride. The sodium, those can entertain the oxygen. So water dissolves sodium chloride. Pentane does not dissolve sodium chloride. It can entertain neither of those ions. Now, that being said, what would water do if it were to interact? What would the water dipole look like if it were going to interact with pentane? Okay. Well, you've probably not really thought too much about it. Maybe you have. Maybe you have. Let's just say. In fact, I'm going to steal this right here. I'm going to steal because that's a nice looking little interaction. So pentane and water do not interact, right? They don't mix. Because if you've got some pentane going on and you got water over here, and I just make the water red, okay, and you got OH, and then that's bonded to an O, and that's got an H, and that's got an H, and that's bonded to an O, and that's an H, and that's an H, and then you got an O, and it's got two lone pairs, so why not, right? You could do that, and these are exchanging, and there's no reason why this isn't static, because you got Brownian motion going on that can disrupt these things, and they're just over here having a hydrogen. They're just swapping hydrogens. They're having a party over here. Pentane is going to present a bit of a problem for that party because this really wants a hydrogen, and that's an oxygen, and that's a then you can imagine the interface right here, and then this water is like, well, what the, where am I going to bond? Like, how am I going to interact with that pentane? And the pentane's like, I don't really care what you're doing, just leave us alone. And the water's still, this isn't like a conniption. It's like, oh, I've got lone pairs. I need to interact. Well, at that interface, water forms a pretty structured environment at the interface between an organic and an inorganic solute. And it forms a pretty structured environment because while this thing, it doesn't matter where the water turns, it's going to find another hydrogen bond donor. Up here, the water can't just like turn and just form a new hydrogen bond with pentane. So at the interface of an organic solvent, water actually starts forming like a meniscus, like that tough outer shell where you've now got a hydrogen here. And it actually becomes really structured, okay? It starts to become super structured in order to form it tries to maximize to the extent of its ability, and you can imagine that, you're going to get these hydrogen networks starting to form. So structure, when it dissolves, or when an organic solution goes in, to a aqueous solution, the water can't get in there, but it forms like a really tight droplet around it, okay? And that's why when you look at it, and you're going to maybe one day go into an organic chemistry lab and you'll see two distinct layers, right? And at the interface between these two layers, you're going to have essentially a very clear line where the water has formed this really structured environment, and looking at the pentane, it's going to have its own sort of interaction, and that's going to be really great for it. Now, as a bonus, I'm going to tell you, right, from Gen Chem you learned about entropy, right? So entropy says essentially if you have a closed system, it's going to go towards chaos. That's just entropy. So if you take water and pentane and you shake it up, why does it separate again? Right? That's not going towards chaos. That's going towards order. So if you have water and you have pentane, chaos says they should just disperse, be completely dispersed, randomly dissolved, but they don't. They will separate neatly. When you shake up a solution of pentane, right, what happens is you end up with a solution of water. Well, you start off, let's just say you start off with a solution of water, and then you got the pentane. And there's like, it's a layer right here, right? So you got solution of pentane, and you got a solution of water. But then when you shake it up, what you end up with is like water, like little pentane droplets, right? Little pentane droplets, sort of little islands of pentane. And they're all sort of like floating in the water, okay? And so what you have done is you've introduced energy into this through your shaking. And what entropy says is it's going to go towards more chaos. And in entropy's head, that's actually going this way, right? So in entropy's head, it's this way. And that is true, okay? Because what you have at the interface of every single one of these droplets is some really ordered, there's some pentane that's living life up to the fullest, right? The pentane doesn't care. It's not going to interact with water no matter where it goes. Well, the water now has this like super ordered, it has to be super ordered because, in fact, I'm not quite drawing it super ordered like I did above there. I think my super ordering was really drives that, but it's going to like, oh, okay, we got to really make a really super ordered hydration shell. And the point is that there's a bunch more of this super ordered water in this particular configuration than in this configuration, right? So there's like a layer of it here, but around every single droplet there's the like high ordered water. And so as a consequence, entropically favorable interactions tend to push this towards separating into two distinct layers. So as it turns out, the separation process into two layers, that is the more chaotic form.